Hi, everyone. My name is Abbas. I'm a researcher at Waabi, and I'm going to go over system safety and verification and validation. So this will be a bit, I'm going to go over it like a bit fast due to time shortage. So in this tutorial up to now, we saw how to build a self-driving system. Now, in this section, we will talk about what a manufacturer has to do in order to convert that self-driving system into a product that can be put on the public road and used to transfer goods or people. One of the main things is just the fact that safety should be rooted in the company culture. So the company should have a positive culture towards safety. It's very crucial, not only to build a self-driving system, but also to maintain the safety level to that critical and minimum risk kind of level. And the organization should understand that the safety is dynamic. So I'm going to talk about what that means. And the organization's cross-team approach on developments, operations, and fleet management must be standardized. As the AV product continues to evolve, it is critical also to keep up with those safety standards and safety level. And this is the responsibility of the entire organization, not just a single team. So if from motion planning side, from detection, perception, prediction, and any component in the safety, in the self-driving system. And it's also important to have timely reporting of performance and safety metrics, because we want to see what is the performance of the system and over time how it's evolving, and if it kind of exposes the company or the product into higher levels of risk that are not acceptable for us. And in that case, we will do some mitigations, which could be just grounding the fleet or things like that. And the organization should also understand what is expected from external agencies while operating on the public road. Now, in order to develop the product, we have to understand what are the requirements from the delivery partners, other drivers on the road, and also regulatory agencies, and also the internal leadership, right? So usually manufacturers use a V-like development cycle, and one of the key things is just creation of the concept of operation, which is just a balancing of what is safe and what is giving more insight into what the capabilities of the current self-driving is. So in order to come up with these product requirements, there needs to be a lot of data. Now, this data can be collected by, for example, the manufacturer itself. It could be real data, or it could be synthetic, or it could be also coming from third-party research or other companies. And these requirements are kind of developed such that it's both on the system level and also on the subsystem level to satisfy the expectations. And there needs to be methods to verify and validate and make sure that these requirements kind of are towards that concept of operations that we agreed on and designed. And this should be verified at each release of the autonomous system. So this is an iterative process. So requirements getting refined and getting more evidence from also operations. And that's why safety is dynamic. It should be kind of updated, and it never ends. When the product is developed, how can we know it's time to take the driver out of the car and let a suite of sensors and compute and actuators control the vehicle? And here is where the structure safety argument comes in. And it has three major parts, which are about architecture, behavior, and operations. And this is used to kind of show that the system has like minimum risk, and like the risk is at an acceptable level. Now let's dive into each of these. So the system architecture should be designed in a way that it can ensure that its reliability and the failure rates are low, and also when failures occur, there is mitigation, and that mitigation can be executed in an effective way. Now, in order to do that, manufacturers follow some standard safety standards, and they make sure that the system is used and operated in an intended way, meaning based on the scoping of the product that we had, and it's never basically placed in a situation that it's not even supposed to handle. Now, within that scope, things still can fail, and it's important to be able to detect those failures and also respond in an appropriate way to those failures. Now, here we have fallbacks that execute some minimum risk maneuvers if needed, and take the system into a safe state. Now, if you have drivers that are supervising the autonomous vehicle, these mitigations can be just taking over, right? Driver taking over the control of the vehicle, or if it's an autonomous system, the mitigation or the fallback could be slowing down or pulling over to the shoulder of the highway, for example. The next part of the system of the safety argument is ensuring that the evidence supports that the behavior of the self-driving car is at an acceptable risk level. And we have basically evidence to support that. And so this involves ensuring that the requirements are developed in an appropriate manner, and long-term are assessed for potential hazards, and ensuring requirements appropriately address each of those hazards. And response to fallback is completed in a behaviorally safe way. Now let's dive into some of those. So when on the road, the vehicle can be exposed to an X spectrum of scenario types. And it is important to ensure that the requirements and tests are designed in a way that it can ensure that the product is able to handle any of such scenarios, from most likely to least likely. And the system is also designed in a way that it can proactively reduce the risk. For example, if it's in a conflicting scenario, let's say it's approaching emerging lane, it can proactively lane change to another lane so that it will kind of reduce the risk of potential conflicts. And the more the system is designed such that we can avoid such potential and dangerous situations, the better we can basically minimize the risk of such hazards. Now, how can we show that we have the right scenarios and we are testing basically on right scenarios, and we know that what the long tail is? So one way is just to collect like millions or billions of miles of data, right? It should be with the same platform, comparable to the in terms of operational domain, should be comparable to the our product. And but this is very expensive, and also at the end of the day, like most of these scenarios that we see in long tail are due to human errors, or they're very human-like. So how can we still now, given this, how can we still make sure that we have covered all the hazards? So we should focus on what could go wrong in a self-driving system. And it's not just relying on the real data or road data and experiences from road data. And most of these road data events could also be very easy for a self-driving car to handle. For example, like it could be due to just distracted driving. So a self-driving car may not be distracted because it's always looking like 360 and is very aware of the surrounding. I'm sorry. Now, there are many parameters that can describe a scene, like an operational domain, and many combinations exist that can describe the scene, and it's nearly infinite. So the problem then comes to how can we approach this coverage problem? How can we make sure that we have tested enough this self-driving system so that we can say, okay, it's very safe. And we have basically covered all those long tail events. Now, one way to do this is to kind of describe, have a model that describes your operational domain in a structured and scalable manner. And utilizing these operational domain and scene taxonomy is the crucial first step. Using such models, we can now query different scenarios by changing the parameters of the scenarios, and then do sensitivity analysis on how, and then using this sensitivity analysis, we can narrow down scenarios to the ones that really affect the self-driving model. And given such scenarios, we can now use a realistic simulation based on the previous presentations and test the self-driving vehicle in those scenarios and see, make sure that we covered those cases, understand what is the performance or the response of the self-driving car. Now, let's look at how we can maximize this coverage over possible scenarios and also understand how the self-driving car performance is in such cases. So in order to efficiently maximize the test coverage, we have developed an approach at Waabi that intelligently generates such scenarios and allows to efficiently maximize the coverage of the and characterization of the performance of the self-driving in those scenarios. So it's a very simple idea. So first we start by just randomly selecting a scenario, basically the parameters of the scenario, and testing the performance of the self-driving car in that scenario. And then, for example, here in that space of scenarios, that star shows a single scenario randomly selected. And then the performance in this case is a bit not great. Now, then we move on to the next step. And in the next step, instead of randomly selecting it, we try to maximize the information gain by choosing the one that gives us more information about the performance of the self-driving car. And this process can be basically iteratively executed and allows us to develop a clear characterization of where the self-driving vehicle is safe and where it can kind of be exposed to high risk. And by this efficient way of validation, we can just test the system in a few places and understand how it does in that a space of scenarios. Okay, so the next thing is the fallbacks. So we try to, by testing, make sure that the system never fails, but it's not guaranteed, right? And the question is, what happens if it fails? So the manufacturer makes sure that the system that is designing does not have a single point of failure. And whenever a failure happens, it can still perform a fallback and take the system and bring it into a controllable state. So in order to do that, it should be able to detect faults, like different faults, and they can have different severities. And it will map those faults into like different fallback and mitigation responses. And these faults could be like severe degradation, for example, something that the vehicle should just like slam on the brake or just come to a stop, or it could be causing the mitigation could be just still continuing the mission, but with a lower speed, because, for example, we cannot see further than like 100 meters rather than 200 meters, which was original like perception range. So, but it's very important that the system can guarantee that either the main compute or the secondary compute can execute these minimal risk maneuvers and bring the vehicle into a safe state. And the last part of the safety argument is operations. So there needs to be training in place for operators so that they know what kind of risks are involved and what scenarios are in the operational domain and what are not, and they can know like when they have to take over and when they can rely on the autonomous system to kind of handle a scenario. And as we scale the operations and as we add more vehicles on the road, we have to make sure that we bring that safety bar higher so that we are not exposed to larger risk level. Now, we have to make sure that we can detect potential hazards in a timely manner. So this is done by producing a few metrics, performance metrics. For example, at the system level or at the subsystem level, let's say we can have metrics about the detection, and over time we will monitor these metrics and make sure that there's no significant degradation. And if there is, there should be kind of actions that prevent the fleet prevent the fleet from going on road. We can basically ground them so that we are not exposed to greater loss. So, that's the conclusion of the safety part. So we talked about like how it's important to have a culture that supports safety. Talked about how to develop a product that basically has safety as its first conditions. And also, like, if you want to deploy a self-driving car, what is the argument about like how safe the vehicle is? And thanks for listening. If there's any questions.
And I wanted to know how do you identify and how do you make sure that we have a full coverage of all the critical scenarios that we have in the vehicle? That is based on what do you think might happen, like what you see in real data,
Yeah. So as I mentioned, there are ways. So one way is just to rely on real data, right? Which was not very interesting because they're very human-like, and you have to kind of drive millions or billions of miles to get them. But if we have a way to describe all the situations that the self-driving vehicle could basically see or be in, then we can kind of parameterize these scenarios and explore this space of scenarios, right? And then intelligently test the self-driving by sampling this space, and then build a model and make sure that we have at least some level of confidence about the performance of the self-driving car in those scenarios.
Yes, if we plan to let I'm pressing the way that other agents might move and change the
Yes, those could be part of the way the model is kind of describes the scene. Yes.
Wondering what inspirations you used to come up with this company culture and processing, things like that, given that we don't have real AV systems deployed with all the military operations or aerospace or something.
Sorry, I didn't get the end of the question.
I was curious, what were some of the sources that you drew from to build up the basically everything that you talked about here, given that we don't have a fully functional autonomous vehicle ecosystem yet for experience to draw from?
The experience what?
To draw yeah, basically, given that we don't have autonomous vehicles or no companies operating them really at scale, what were some of the inspirations that Waabi used to build the safety program?
In terms of culture. So I mean, basically, I would say it's like thinking about what catastrophes can happen, right? If we as a company putting a self-driving car on the road, we are responsible. Everyone is responsible to make sure that whenever we see something, we basically that can kind of be increase the risk, right? Risk of any kind. We are encouraged and allowed, and no matter what level we are at, right, in the company hierarchy, we are encouraged to talk, and we are kind of encouraged to talk about it and ask questions and be kind of be proactive about the decisions that are made. And it's a very transparent culture, so it's a very transparent process, and anyone is welcome to kind of question specifically these kind of safety critical decisions. So that's one thing I can say.
All right. This brings us to the end of the tutorial. Thank you all very much for attending, both online and offline. Thanks for sticking through with us until the end. Stay tuned for updates about things like slides and recordings and stuff. We'll do our best to kind of gather and organize this information, so you can check either our social media like Twitter or the website for the tutorial that you can find through the CVPR platform. And be sure to check there after the conference for any updated materials. But until then, thank you very much for attending. We're happy to explain all this stuff to you guys. All right, good work, everyone.